Yeah, hopefully online everyone can see and hear. So yeah, welcome to the Epic Kitchens and HD Epic Challenge results and talks. So this is the 7th year for Epic Kitchens, started in 2019, and the 1st year for HD Epic, so we're really happy to present these. So just a bit more information about the session. I'll go a quick overview for the VQA benchmark for HD Epic, as it is the 1st year that it's running. We'll go through some challenge results and winner announcements. I'll say we're only going to kind of have the winners that are presenting talks kind of receive the certificates. Otherwise, you can see the rest of the winners on the website. And then we'll go through 3 selected talks, 5 minutes each of the ones that we selected for the workshop. So HD Epic is our dataset that we released earlier this year, and it's going to be presented at CVPR. It's a collaboration between everyone at Bristol, University of Leiden, Singapore Management University, and the University of Bath. And it started with, as with all datasets do, with a bag full of devices given to participants. We gave them 4 ARIA glasses to record over 3 different days. We had a power bank, a phone to check what they're doing, some weighing scales, which I'll talk about later, and some recording instructions. So they used these to record every time they went into their kitchen over the course of 3 days. So you can see here in the boxes, these are when participants went into the kitchen, so they recorded these sessions. And once we had these recordings, we then looked at 3 different main types of annotations to go along with this. So the first, which is new within HD Epic, is the different recipes. So we asked people to collect the recipes and the steps that they were doing, as well as the nutrition. So we kind of have all these temporally localized steps of when people preheated the oven, prepared their potatoes, and so on. So we have the steps themselves and the preparation. So you need to pick up your sweet potato before you can wash it, and so on. We also have the weighing and nutrition information that participants collected to go along with all the nutrition and the recipe information, and when this kind of gets added to the recipe. So in total, we kind of have these recipes that were being collected. We asked participants to take online recipes and then modify them based on the different units of ingredients that they used, or maybe they changed out different types of ingredients. They also modified the steps based if they kind of changed them or did them in a different order. So we have, like I said, we have these preps and steps. So when did you prepare something and when did you actually complete the step itself? And we have these temporarily localized through the videos, so you can see when people did each prep and step. As I said, we have weighing for the scales, so each participant weighed their ingredients, so we have the exact amounts that they used, and when they added this into the recipe, so this is the weighing step, and then later when this got added, so we actually know when the recipe, kind of the nutritional information got added to the recipe. So the next set of annotations that we have were kind of the fine-grained annotations. So similar to previous versions of Epic Kitchens, we have these narrations that we asked the participants to record after the fact, but with a lot more detail. So these are much longer, took a lot more time from the participants. And these were kind of had the start and end times as previously. We got the verbs and nouns, but then also expanded this with the hands, the how, and the why people are doing things, so we can get this very fine-grained understanding of what is going on. And like with previous versions of Epic in Epic Sounds, we have the audio annotations as well. And just to kind of give a sense of how much more detailed these are, especially playing real time. So this is one of our videos that you can see how quickly and how much detail the narrations go through in the video. Okay, and then finally we kind of went beyond other collections as well to move towards 3D and moving objects. So what does that entail? Well, we have the objects kind of localized spatially throughout the video. So this is an example of a sweet potato and how the person is interacting with it. And this kind of goes beyond the whole sweet potato and also the chunks. And then we can do this for a lot of the interactable objects within HD Epic. And then the final kind of aspect as well is kind of creating a digital twin. So all of these annotations can kind of live within this. So we have the point cloud from ARIA machine perception services from the recording. So you can see that's kind of the camera moving through the scene within someone's kitchen. We have the surface, and then we asked someone to recreate these inside a digital twin, and we have all this fixture information as well. So you can see here how we're going from the point cloud to the mesh to the fixture annotations and so on. And then we can also keep track of the objects throughout the scene. So these are all the different types of annotations that we have within HD Epic. This kind of gives us a total annotations of 263 annotations per minute, hence the name highly detailed. And so there's a lot of information here that we hope the community can use. So that was one aspect of the paper that we'll be presenting. The other aspect, which is perhaps more relevant to this part of the workshop, is the VQA benchmark. So this was created alongside the dataset to kind of test these large vision language models. So we have 7 different types of questions which are based on the different annotation types: the recipe, ingredient, nutrition, fine-grained actions, 3D perception, object motion, and gaze. And we tested a variety of different state-of-the-art vision language models, including some blind baselines. And what we noticed is that even though some of the recipe questions kind of get answered pretty well by the models, there are a lot of questions which the models struggle with, even kind of the state-of-the-art ones. And all of them are well below the human baseline. We also looked at the effect of input length, so it might be expected that shorter videos or even single frames should be performing quite well on these models, but we find that that's still not the case. They still lack the fine-grained understanding, even for short video lengths. And finally, we find that all the models are biased in some way towards question type, so the ideal, we have 5 answers, so they should choose each answer around 20% of the time. We find in reality that they are still biased towards some of the answers. Okay, so that's the data set. We have a website. If you want some more information, we have a demo on Friday, and we also have the poster presentation itself on the Sunday. So come ask us there, or if you see anyone with a HD Epic badge, feel free to stop us in the corridors and ask us about the data set. Okay, so on to the challenge results and winners themselves. So like I said, we have one challenge from HD Epic, and then we have a variety of challenges from Epic Kitchens. So 3 of the challenges from Epic Kitchens, the participants weren't able to beat the baseline from previous years. So whilst we had active participation within this challenge, they weren't able to beat previous year's baselines. But for the rest of the challenges, we had people beating the baselines. So let's go a bit through the HD Epic challenge. So there was no hidden test set for this, and whilst there are 26,000 questions, these are all treated equally. We had 2 teams that were submitted to the leaderboard, so that's Deep Frames and Hello World, and they were able to kind of beat the baseline Gemini, which was the best performing baseline from the paper. So they kind of get a nice improvement in motion as well as 3D, but there's gaze and kind of other aspects which require a bit more push from the community. In terms of the Epic Kitchens challenges then, so despite frequent attempts, and we can see the statistics of people submitting new methods, these baselines are now getting harder and harder to beat. So you can see on the right that we have had community participation. It's just since 2024, where there was quite a boost in performance, this is kind of flatlined for this year. And this is the same also for action anticipation, which had a nice boost in 2022, but then has not been able to beat previous baselines for the last few years, despite a lot of participation in this area. And also for action detection and unsupervised domain adaptation for action recognition, which we believe is due to features kind of not really having been improved and kind of the saturated benchmarks. So this kind of raises the question on how do we fairly compare. So most people, if they don't beat the baseline, it's common not to report the result at all, whereas you might be using different amounts of data, different pre-training regime, and so on. So Dima and I had this paper from a few years ago now, which tried to kind of solve this, but this hasn't had too much uptake from the community, so maybe there's something else that we need to do to try and push people to still showcase their results and still validate improvements, but using different training regimes, amounts of data, and so on. So the benchmarks, we did have a couple with minor improvements. This is mainly the Epic Sounds benchmarks. So we had a 0.3% increase on the detection task, so quite a hard task, and 0.2% on the interaction recognition task. Other benchmarks had visible improvements, such as the semi-supervised video object segmentation, as well as the multi-instance retrieval. So this was the first year for them to pass the 90% and the 80% respectively. Okay, so we're now going to do the prizes for the winners' talks today. So that's the top one, HD Epic, where I believe they're online. So if I go back to the Zoom session. I don't know if the winners of this team, so this is the first place award. If you want to, hopefully everyone can see this. So I think if someone's going to take the pictures for this, yeah, and I think Chiara, are you coming up as well? So yeah, this is the first place award, which is down from Politecnico di Milano and Essilor Luxottica. Sorry for the pronunciation. So if we stand in front of the screen so we can capture that. And then next we have the second place for the HD Epic VQA challenges, which is from Huawei, Noah's Ark Lab, Queen Mary, University of London, and Imperial College London. I believe someone is in person to collect the prize, if you want to come up. And then finally, for the semi-supervised video object segmentation, I believe, again, this is virtual. So if you can unmute, where did the Zoom window go? Here we go. Yeah, I think, yeah. Yeah, in front of the camera. Yeah, that's probably the best thing as opposed to me jumping up. So a round of applause for the final team. Okay, so now we'll go to the talks themselves. Yeah, so if we have the top one HD Epic team, if you want to present, if you can hear me.
Screen?
Yes, please.
Okay. So, hello everyone, I am Angese, he's Davide, and we are master students from the Politecnico di Milano and the Smart Agro Lab, which is a joint research center with Essilor Luxottica. Today we will present a work from pixels to graphs using scene and knowledge graphs for the HD Epic VQA challenge. So egocentric video understanding, as you know, is challenging. It requires more than visual frame-by-frame analysis due to fast motion, occlusions, rich temporal dynamics, and complex interactions with objects. To tackle this, we decided to use structured intermediate representations to help models reason effectively over time. This approach naturally leads us to neurosymbolic AI. What is neurosymbolic AI? Neurosymbolic AI combines the strength of neural network-based methods with the power of symbolic knowledge-based approaches. So it effectively augments the strengths of neural networks with human-like symbolic knowledge and reasoning. This is our methodology, which consists of two parallel configurations. The first one is a CNET, so we prompt the multimodal large language models with a schema, starting from video segments, to obtain a graph which captures fine-grained object interactions and spatial relationships. And this graph is directly grounded on video observations. The second configuration is a knowledge-net, where the graph is grounded on external knowledge instead. So starting from objects detected in the video, we expand this common sense. We expand with common sense knowledge, encoding object affordances and semantic associations. Here is our full pipeline. So we feed these structured graphs along with the question into the multimodal large language model to produce the final answer. An important detail from our experiments, which we will discuss later, is that for CNET, we do not pass the raw video because the graph is comprehensive, while for KnowledgeNet, we do pass the video together with the graph to help connect the external knowledge with the specific visual context of the scene. So this is an example of a CNET graph. It explicitly model nodes like the agent, so the person recording, environment nodes for the static layout and objects like the refrigerator in the kitchen, and dynamic objects like the mug or the milk carton. So this scene graph also models hierarchical and spatial relationships among these entities, like the fridge door is part of the refrigerator and the mug was initially located on the main counter. Finally, we have the action hyperedges. Here the action is pour liquid from to with a specific timestamp associated. So this action hyperedge links the participants, the performer, the source object and the target object, and the resulting state changes of the linked objects.
In KnowledgeNet, we build an object-centric common sense knowledge graph. Specifically, we build a graph for each object detected through zero-shot object recognition with a multimodal LLM, such as dishwasher. We then expand the graph with the common sense knowledge from ConceptNet based on the object affordances. And finally, we serialize the graph into semantic paths to be injected into the prompt, such as dishwasher is used for washing dishes. The overall accuracy comparison shows that both methods outperform our video-only baseline. Specifically, CNET in categories require fine-grained spatio-temporal understanding, such as recipe, object motion, and 3D perception, while KnowledgeNet, where external procedural knowledge beyond visual cues plays a key role. Finally, our final submission consists of an example with best-performing model per task. We conducted evaluation studies to assess the impact of providing additional input to the model, specifically the video alongside the question and the symbolic representation. We report the overall accuracy on a random subsample of 50 samples per microcategory, highlighting that providing video input improves performance only for KnowledgeNet because of the importance of grounding the symbolic knowledge in visual context, while for CNET, the symbolic representation is often sufficient. And finally, in the hybrid approach, performance was lower than that of the individual models, mainly due to the weaknesses of each component. Indeed, CNET is better without video, whereas for KnowledgeNet is the opposite. So by combining them, may sometimes introduce excessive or relevant information. To conclude, we propose a graph-based approach for visual question answering, showing that incorporating a symbolic intermediate representation improves the reasoning capabilities of multimodal LLMs, and a promising direction for future work is to integrate both CNET and KnowledgeNet into a unified and more harmonized framework, leveraging their complementary strengths. Thanks.
Okay, thanks a lot.
Thank you.
Hi everyone, my name is Jiankang Deng from Imperial College. Today I will help my two master students to present their solution for the HD EPIC VQA challenge. And we optimize the multimodal LLMs for the egocentric video understanding. So our contributions include the main three parts. The first part is the processing step. We propose question intent recognition and clarification. And then we fine-tune the open source model Queen 2.5 VLCMB on annotated egocentric kitchen dataset. We also propose the temporal chain of thought method to deal with the long sequence. Finally, in the post-processing step, we propose the prompts ensembling. Here, we choose performance improvement for each component. As we can see, our method starts from the Queen 2.5 7B model, our pre-processing step, fine-tuning step, and temporal chain of thought, and post-processing steps, or significantly improve the performance. Our final result is 41.6%, outperforms the baseline method Gemini Pro 37.6. So let's start from the question intent recognition and the clarification part. So we first analyze the input modality, and there are different tasks based on single image, multi-image, multiple videos, and we design task-specific prompt refinement. We found that when we optimize the structure of the multiple choice options, such as we use the ABCD, this prompt directly increases the performance by 1.6. And we also found that the new line character can further improve the performance by 2.4%. In total, the pre-processing step increased the performance by 3.5%. And then we fine-tune the model by using the Queen 2.5 VR7B model. And here we choose detailed learning strategies. And we fine-tune the model by 1 epoch on 6 egocentric kitchen dataset. We only fine-tune the LLM model, keep the vision tower and the MLP projector freeze. And the maximum frame number for each example is only 768. Then we propose the temporal chain of thought method for the localized vision information, such as a bounding box or specified time points or segments. We use a noun phrase to substitute those information. For a window around the key event, we dynamically segment the video into shorter videos. And for multiple video clips, we concat them together. For fine-grained and detailed understanding, we generate a narrative description for the trunks. And for post-processing, we parse and extract the most probable single letter choice, and we tried 5 semantic equivalent prompts per question. And the majority voting finally improved the performance by 0.8%. So here we list the final result for different tracks, and our method achieves the best performance in 10 out of those 30 tasks. In conclusion, we enhanced the multimodal LLMs for egocentric video understanding by integrating structured input, output, and domain adaptation by fine-tuning, guided temporal reasoning, and prompt ensembling. In the future, we will consider to scale up our model to 32B or 72B. Currently, our model training are constrained by the computation resources. So we expect to have a further performance gain in the future. Thanks.
Okay, I think in the interest of time, we're going to move on to the last talk. So yeah, thanks a lot for presenting.